Hey, Chris, I sent a meeting out, a message out saying that I wasn't going to start till 7:40, but I was afraid some people might not have got it. So I'm just going to sit here until then. Actually, if I get a couple of you, I might go ahead and give y'all an intro and y'all can split and we'll see how that works out. Looks like it might just be you. I could still do the same thing. Yeah, it looks like you might be the only one that's going to show up at this time. Can you hear me, Chris? I turned your speaker on. Can you hear me, Christopher?
I can hear you, sir.
Okay. I'll go ahead since nobody else is here. I'll go ahead and give you an intro, and then you don't have to come back later if you don't want to. It's no big deal. So let me start. I'm going to try to change cameras so you can see what I want to discuss. Basically, this lab this week is called the Photoelectric Effect, and it's actually basically based on an experiment that Einstein suggested they do in 1905. 1905, Einstein wrote 4 different papers, and all 4 of them had the ability to have won him the Nobel Prize. This is the one he actually won the Nobel Prize for. He wrote a paper on Brownian motion, which was the first paper proving conclusively the existence of atoms. And he did that with statistics that was pretty amazing. He also wrote a paper on special relativity. It's called the electrodynamics of moving bodies. And that one, of course, he could have won the Nobel Prize for. Then he wrote, like a couple days later, he wrote, oh, by the way, here as an appendix, here's this E equals mc squared thing. That actually proved how the sun was working. Could have won a Nobel Prize for that. And he wrote the photoelectric effect paper, which is a founding paper for the quantum mechanics. So this lab, you're going to actually, well, since you're not actually doing it, you're just going to take the data that we have. But I wanted to explain to you guys what the photoelectric effect was and what you're supposed to get out of the actual lab. Those of you just came in, Scott and Zarni, I told Christopher that I delayed it till 7:40, but since you are here, I'll go ahead and intro it again, and I'll start back over once we're done. But you guys are free to go when I finish explaining the lab to you. It's called the photoelectric effect, and let me turn the document cam on. I didn't mean to do that. Oops. Let's see how decent this looks. Okay, so that's not too terrible anyways, as I can see there. All right, so basically a guy by the name of Planck came up with this idea. Basically, we knew that when you make a plot of the energy put out by something that was heated, so you make a plot of energy versus either frequency or wavelength, okay? It turns out that the curve for that type of thing looks like this. It's got a gradual slope. It reaches a peak, and then it has a quick drop off. If I did it versus wavelength, the steep part would be over here, and the gradual part would be over here. And we had a hard time describing that. There were people that made up equations that described this part. There were people that described this part, and there were other equations that had described this part. But none of those equations matched one another. What he did was he pretended, and this is a common thing we do in physics, he pretended the atoms were actually connected to one another by springs like this, and then there'd be another spring here, and then there'd be another spring here, then there'd be another spring here, and then of course going back behind that there would be springs like this, springs like this, a spring like this, and then a spring like this, so on and so forth. And in doing so, he was allowing them to oscillate when they were hit by waves. And what he was trying to do is see what energy would be radiated at what frequencies. Well, one of the tricks that we used to do back in that time was when you had a variable like, let's say, frequency that could literally be anything from 0 to infinity, you might pretend that instead it's 0, 1, 2, 3, 4, 5, 6, 7, 8, up to infinity, but none of the numbers in between. So he did that, and what it is, it allows you to do some really difficult mathematics easily, and then in the end, you take the limit as the quantity that separates the consecutive values goes to 0, and you get basically back the original equation as if it were a continuous variable. So what he did was he said, let's pretend E is equal to N times some constant times F, where N would be equal to 0, 1, 2, ... So that was what he actually hypothesized. And then it kept looking promising, but then when he did the little limiting process that allowed him to make this become a continuous variable again, it always failed. So he said, heck with it, I'm just going to assume it works. I don't know why. And he basically published his paper like this, and that actually gave exactly the right curve. So this was called the quantum hypothesis. It basically said that the amount of energy that could be given off by these atoms when they're vibrating can only be 1 times some constant times the frequency, or 2 times some constant times the frequency, or 3 times some constant times the frequency, so on and so forth. And the 0 doesn't really mean anything. So that was Planck's quantum hypothesis. And with Planck's quantum hypothesis, Garrett, I'm going to start this back up again in a few. I just went ahead and started for the people that were here so they wouldn't have to stay too long. So with quantum hypothesis, we got this new idea of energy as being equal to the frequency of the wave, or the frequency of the waves of energy coming from it, times some constant. That constant turned out to be Planck's constant, and it's 6.626 times 10 to the negative 34th joules. That's 34, by the way, joules times second. Okay, we've now called that Planck's constant. And that's sort of the one fundamental equation you need. So Einstein realized, okay, well, this is actually treating light as if they're little particles of light, but also as they're waves, because we'd more or less gotten through all of understanding of light by Newton by treating it as if it was particles. So here's a way where you could relate something as particles as related to waves. So Einstein's big idea was, hey, let's attack this photoelectric effect. And the photoelectric effect was basically when you shine light on a metal, preferably a pure metal, it will actually give off or create a current in the metal, meaning you don't have any batteries connected to it or anything else. You just basically get a current reading across it. And they could explain that with treating light as if it were waves, but the problem was you'd expect if light was actually a wave, the brighter the light, the more radiation would come off of it, and that wasn't the case. In other words, the more current would be derived, the brighter the light was. And not only that, there would be a delay that no one had seen, and a lot of weird stuff. So Einstein attacked it as if it was using this quantum hypothesis, and he basically said there's probably some minimum amount of energy that you have to be able to supply before you can knock an electron loose from an atom. And he would say E min is that quantity. And it, of course, would be equal to what he called the work function. And that is basically a property of the material. So you get a work function for aluminum, you get a different one for steel, you get a different one for copper, something like that. But then he said, well, actually, since the energy is going to be proportional to the frequency, then what he thought would happen is that you would actually get an amount of current that would actually be produced would be directly proportional to the frequency plus this work function. So basically, he's going on the assumption that if you made a plot of current versus temperature, or excuse me, versus frequency, there would be some minimum frequency at which current would actually happen, and then you get a straight line after it. So that's Einstein's hypothesis. Lo and behold, and by the way, this is related to the work function. Obviously, it's frequency, so it can't be exactly the work function, but it's let's say the work function divided by h, or something like that. So that's sort of what we're doing here. You'll get a better explanation for it in the actual lab manual. Also, you can look up the photoelectric effect in your textbook, but I just wanted to give you a little intro to what we're doing. So what you're going to try to do, and in some labs, by the way, we plot it as current versus frequency, and others we plotted as energy versus frequency, because the idea is this: you're going to have a minimum amount of energy that's required to create the current. That's going to be given by h times frequency, and that's also the work function. But as the frequency gets higher and higher, basically what happens is those electrons that come off not only create a current, but they actually go a little bit faster. So the extra energy goes into the energy of the electron. So if you plot energy, you get a similar type relationship. So in this week's lab, let me share my screen with you real quick. In this week's lab, what we're going to do is the photoelectric effect. And I think I can see it from here. Yes, this is it. So I'm going to go back to my modules. And what we have here is quantum mechanics, the photoelectric effect. So I know everybody's taking 242. You might find reading the 202 one easier, and then use the 242 one is what you have to do. But you're just going to download this document. This will tell you how to do the lab. And you can see it's just a PDF. Let me minimize this screen right quick. So here's the theory. You hit a screen with a ball and it bounces off. If you want to break through the screen, do you throw more balls or do you throw the balls harder? So that's getting your idea into, let's not think about the brightness of the light. Let's think about the number of, or the energy of the individual particles that are hitting it. That's what that's asking you, that first one. If you want more holes in the screen, do you throw more balls or do you throw the balls harder? So that's looking at it from the other perspective. What is the formula for energy of a single photon in terms of frequency? That's the E equals HF I just gave you. If you change the color of light, how do you change the number of photons or the energy of the photons? Well, it turns out changing the color of light is either changing the frequency or the wavelength, or technically it's both, because the frequency times the wavelength always has to give you the speed of light. So if you change the frequency, you're also changing the wavelength. So that gives you a little idea of that. If you change the brightness of a light, do you change the number of photons or the energy of the photons? I think you can guess that now. And the energy to ionize electrons is called the work function. That's what I just talked about. What is the electron's kinetic energy, K, in terms of the photon energy? And the work function, W. And then replace the photon energy using its formula, see above. So right here, this is one of those PHET simulations like I told you guys about. So that gives you a website that you can actually go to. You're going to click on this, and you're actually going to conduct the experiment in a simulation type environment. So that's all you guys got to do. If you'll notice in the module, go back to that right quick. You've got a place to turn it in. This is where you're going to turn in your lab results, and that's what I'm using for attendance. Same thing with the gas law lab. You turn it in here, and I use that for attendance for that lab. And the half-life lab, you turn that in here. Interference lab, you turn that in here, and that's it. Any questions on that, folks?
Sounds straightforward.
Yeah, it's not too bad. Like I said, you might look in your textbook and the chapters on quantum mechanics. It'd be the chapter on early quantum mechanics. That's where they talk about the photoelectric effect. So if you want a little bit more background story other than what the little junk I gave you, check that out. Other than that, you guys are free to go.
Thank you. Have a good one.
You too. Stay safe. Garrett, I'll start back over with you, bud.
Yeah, I have a quick question about
Yes,
for the test in the lecture class.
Uh-huh.
I said to electronically sign the honor pledge. I don't know if I missed that, or where was that?
It should have been a question at the very bottom that just had a multiple choice. You're supposed to put click on the answers, and there's no actual physical signature.
Oh, I might have missed that. I'm sorry. Might have been a mistake. Rushing to finish.
Yeah, the very last question, there should have been 7 questions, and the last one's worth 0 points. And it just says, I did the following, and then you have A, B, C, or D. So you didn't see that on there at all?
I don't think so. If I did,
check. That might have been something I left off. That's okay. It's I'll probably just send out or ask you to write an honor pledge and sign it and send it to me.
All right.
All right. Don't worry about it, Scott. You're good.
All right. Thank you.
You're welcome. See you. Hey, Garrett, what's going on, bud? Is your speaker working? I guess Garrett's speaker's not working. Kaylin's coming up. What's happening, Kaylin? We're supposed to start in about 7 minutes. I had asked everybody to hold off till 7:40. I'll start over again in a second. Hmm. Got about 3 more minutes and we'll get cracking. Ooh, more pokes. Hmm. Cat hair all over my computer screen. All right, I guess we'll go ahead and get started. So, everybody, we're doing the photoelectric lab today, and this is one of the beginnings of quantum mechanics. So normally this course we'd finish up with electricity and magnetism, and then we jump into, there's a chapter called early quantum theory or early quantum mechanics, something like that. Then there's quantum mechanics, and I think there's a third chapter on quantum mechanics about the quantum mechanics of atoms, and then we go from there to possibly nuclear physics or relativity or something like that. Sometimes we put relativity in the first semester, but we won't be able to get to all that stuff. But we did want to expose you a little bit to quantum mechanics. So that's what this lab's about, and it's called the photoelectric effect. So in 1905, Einstein wrote like 4 or 5 papers all in that same year, and probably everyone would have qualified him to win a Nobel Prize. The one that actually did win him the Nobel Prize, though, was the photoelectric effect, which is the experiment you're going to be running today with PHET. So the photoelectric effect, to give you a little intro about that, I need to start off by explaining to you what Planck did. So in late 1800s, early 1900s, if you surveyed maybe all the physicists, all the scientists, chemists, and everything in the world, they would probably have told you at that time that they were pretty much just sweeping up, making sure everything that Einstein predicted was right to 4, 5, 6, 7 decimal places, and that they had figured the world out. Well, there was a few things going on that hadn't quite been worked out, and they thought they were just going to be a matter of time to figure that out. But it turned out there was 2 major revolutions coming on. One was the special theory of relativity, which no one saw coming at all. one of the marks of a genius is not their ability to solve a problem that no one else solves, or not their ability to hit a target that no one else can hit, but rather to actually see a target that no one else sees. And that's what Einstein did with his special theory of relativity. He saw a problem where no one else saw it. And not only did he see the problem, he solved the problem. So it was pretty brilliant in his special relativity paper. And then, 10 years later, he comes back and actually 6 years later, he comes back and publishes his general theory of relativity, which is still making predictions that are just now being confirmed. But in 1905, basically, we had some things going on, one of which was something called the UV catastrophe. So I'm going to switch right quick to show you my document cam. So turn this to the document cam. And basically, when in the early 1900s, let's make sure I can get this into focus. In the early 1900s, there was this graph that people would make. So basically, if you take like let's say a horseshoe stake. Oh, Janie's here, hold on. So Janie's coming on, hold on everybody. All right, so we're talking about the photoelectric effect. And what I was saying is in the early 1900s, there was a few experiments that people couldn't explain. One of which was the photoelectric effect. And another one was the ultraviolet catastrophe. And another one still, man, I just realized my dog ruined my pen. Another one still was actually something called the spectra of compounds, which is kind of a weird thing. But the first one was solved by a guy by the name of Planck. So if you actually take and make a plot of energy, so you take a horseshoe stake, made of iron or something, and you actually heat it up. And then you take that light coming from the heated up horseshoe stake and run it through a prism, then the prism would break it up into several colors. And if you measured the amount of energy that came out from each color, and by the way, color means either frequency or wavelength, you can do either one. But if you did that and actually did a plot of energy versus wavelength, then the graph would actually look like this. It'd be really steep on this side, reach a peak, and then it would gradually fall down on this side. Everybody knew this was what was going on. The problem was we had equations, Rayleigh genes and stuff that could handle this. They had equations that could handle this. They had equations that could handle this. But the three different or multiple different equations didn't match each other, and they certainly didn't fit together. So they called it the ultraviolet catastrophe because this curve right here was expected to go on forever. But by the time you get out here to the UV light, you see it's supposed to roll over, and it didn't do that. So this guy by the name of Planck had this idea, and it was sort of what everybody was doing. Everybody was trying to model atoms and molecules as if they're little balls connected to one another on springs. So you'd picture an atom, an atom, an atom, an atom, and then back behind that is another atom, and another atom, and another atom, and then one back here. And then you say, well, they're connected by springs. And then that row back there is connected to this row by these springs. And then, of course, they're connected again, just like these other ones are. And when you do that, you basically say, okay, when radiation or something hits this, it's going to cause those springs to oscillate. Wingle, 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 like that. And you got to make a silly sound when you do that. Wingle, 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 right? So the deal is, the idea was, hey, let's imagine what happens when this radiation, which is, let's say, a wave, hits these actual atoms. It's going to make them vibrate in sympathetic motion, and that's going to cause photons of energy to come out of it. And their idea was, okay, well, let's do that, and then we should be able to find all these energies for all these different frequencies that these springs can oscillate at. Well, he was trying to work up an equation that gave all this. So he used a fairly popular trick of the time. He imagined that the energy that would come off from these things vibrating was not a continuous variable, like, energy could go from 0 to infinity. He imagined it was like discrete, like energy could be 1, 2, 3, 4, but nothing in between 1 and 2, or between 2 and 3, or between 0 and 1. And he did that by saying it's equal to n times some constant times the frequency. Now, by the way, when I put the lambda over here, that's the wavelength, and wavelength increasing is the same thing as frequency decreasing. So frequency is decreasing this way, wavelength is increasing that way. The reason why that's so is velocity is equal to frequency times wavelength, and the velocity for radiation is always the speed of light, so that's fixed. So if this goes up, then that one's got to go down by a similar amount, so you still get the same speed of light. So he said this, and with this idea, that n has to be 0 or 1 or 2, and of course 0 is trivial, so you wouldn't even consider that one. And this was just a constant. He didn't know what the constant was. We've since determined experimentally that what its value is, and we now call it the Planck constant, and its h is equal to 6.626 times 10 to the negative 34th joules times seconds. So that's the actual Planck constant. Double check me on it just in case I, did something goofy or remembering it. And we use a bunch of different units, so sometimes I forget stuff in different units. But anyways, that's now called Planck's constant. And what we see is the energy is actually proportional to the frequency. That means if the frequency goes up, the energy goes up. So that was what we call the quantum hypothesis. And what made it quantum was the fact that there was certain allowed energy that could come out, 1 times HF or 2 times HF or 3 times HF, but nothing in between. So it's sort of like if you look at a digital speedometer on your car, when you hit the accelerator, it looks like it's skipping speeds. Imagine if that was reality. Imagine if those speeds that it skipped were skipped because those speeds are impossible to get. Not the high end, just in between 12 and 19 miles per hour, there's no speeds that you're allowed to get. That's what quantum is talking about here. So it's really kind of weird. So Einstein saw this paper, and of course, Planck won the Nobel Prize for this as well. But Einstein saw this paper and said, oh, I can use that to solve the photoelectric effect. Well, the photoelectric effect was basically, scientists had discovered that when you shine light on a metal, a pure metal, it will actually create a current. Now, if you treat light as a wave, that makes some sense. And in fact, you can do calculations, but you'd expect certain things. Like the more light, i.e. the brighter the light that lands on the metal, the more current would be produced. And there'd also be sort of a time delay, which wasn't observed either. So that was kind of weird. And basically, as long as you made the light, it didn't matter what color it was, i.e. what frequency it was. As long as you made the light bright enough, it would derive a current, and that's not the case at all. So Einstein said, well, let's imagine these photons of light, these particles coming in. They have to have some minimum amount of energy to actually knock an electron loose from the atoms in the metal. And remember, that's what conduction is. When a current is conducted, it's actually electrons moving freely through the metal. So his idea was, we'll say, let's do an experiment where we actually measure how much energy it takes to stop the electrons from flowing. In other words, you put a battery, maybe you measure current on a piece of metal, and you measure the current going this way. So now maybe you connect a battery trying to force the current to go the other way, only you allow it to be adjustable. So it's got a knob on it so you can adjust it. And you adjust that until you make the current go to 0. If you did that, what would happen? Well, according to Einstein's idea, what you'd get is basically when you turn the voltage up just right, it would actually stop the kinetic energy of the electrons and therefore stop the actual current, so you get a current of 0. So what he made was an idea of the actual energy. So the energy of the electrons would be equal to H times F, but there would be some minimum amount of energy that was required to actually cause the current to overcome this, or excuse me, cause the atoms to lose their electrons, and that amount of energy would be subtracted out. And sometimes they use the symbol phi like that, sometimes they use W, or sometimes they use phi like that, but it's called the work function. And it's a property of the material. So for instance, if you did this experiment with aluminum, you get one work function. If you did it with copper, you'd get another, and gold another, and stuff like that. So if you look at this and you consider what would the actual energy as a function of frequency look like, it would look like this. And this would be indicative of your actual work function. That's what you're going to do with this experiment today, is you're going to sort of generate this graph using PHET. So the equation you really need here, guys, is E equals HF, where H is that Planck's constant. And now let me show you the lab so it makes a little bit more sense what we're talking about. I'm going to stop sharing my screen. No, actually, I'm going to share my screen. That's what I'm going to do. And I'm going to go to here. Stop sharing my camera. That's what I'm going to do. And what I wanted to show you is what the lab is actually requiring you. This is where you're going to turn it in, just like that was where you turned in the gas law. That's where you turned in the half-life, and that's where you turn the interference lab. So make sure you turn all those in. That's how you're getting credit for attending these last labs. But let me show you what this thing says and walk you through a little bit of it. So right here it says quantum mechanics. You hit a screen with a ball and it bounces off. Let's imagine you're throwing ping pong balls or something like that at a screen, like screen in the screened-in porch. If you want to actually break through the screen, do you throw more balls at the same speed, or do you throw the balls harder? I think y'all can see that obviously throwing the ball harder would have a better chance, even though a ping pong ball might not ever break through a screen, but you certainly have a better chance if you can throw it harder. So that's sort of the difference between how people were looking at the brightness of light hitting a metal. That's more photons of light hitting it versus the speed of the photons hitting it, which is given by h times f, because basically energy is h times f according to Planck, but that energy goes into kinetic energy, which is normally like 1/2 mv squared or something like that. So you can see they're making the argument that it's probably easier to break a screen by throwing the ball faster than it is by throwing several balls at the same speed that you were before. If you want more holes in the screen, do you want to throw more balls, or do you want to throw the balls harder? I think y'all can figure out that that's sort of the opposite look of what we did in the first part. And then it asks you in this third part, what is the formula for the energy of a single photon in terms of frequency? That's the equation I just gave you, E equals HF. Since velocity equals frequency times wavelength, and we normally say velocity for the speed of light is c, then you could also say E is equal to hc over lambda, but that would be hc over lambda would be the equation giving it to you in terms of wavelength instead of frequency. So he's wanting, in this case, E equals hf. Now it says, if you change the color of light, do you change the number of photons, or do you change the energy of the photons? Well, I already hinted to you what the actual color was associated with. You either associate that with frequency or with wavelength, and the two are always related, because if you multiply the two times each other, you get the speed of light. So I think you can figure out what's changing when you change the color. If you change the brightness of the light, I think you can tell what changes as well. And finally, the energy to ionize the electron is called the work function, W. What I called phi, I also showed you was W. What is the electron's kinetic energy, K, in terms of the photon energy, and W? Replace the photon energy using the formula that you found up here involving frequency. So now all you have to do is go to this website, which has got a link for you, and it's going to tell you how to change various things and play with certain things. But at the end, you're just going to be able to do this experiment using simulation software. So you just click on this and start running it, follow the instructions, and it's, I did not want to do that. I tried to play. Oh, no wonder I hit play. This might be one where you actually can't play it. You have to download it. Let's see. No, it looks like it's acting that way. So that might be the case. You might have to actually download it. I did not write this lab, so I'm not sure. Oh, I see. It does take Java, by the way. So make sure your browser has Java. But all you have to do is follow this setup, click on download. If any security dialogues come up, accept them. This is a safe site. This was created by the University of Colorado at Boulder. And then they give you steps by steps, and you'll actually get really perfect results, because the simulation is a perfect simulation as opposed to being dealing with experimental error and stuff like that. So I think that should help you guys figure out what to do on this one. Does anybody have any questions before I let you guys go?
Yeah, I had a question for
Monty.
For the let's see, for number 3 on lab 11. It was finding the percent error. It is just a matter of finding what am I looking for, because I went to the first page and I was trying to find exactly what I was looking for.
So which lab were you talking about? You talking about the one on the gas law?
No, the half-life.
Oh, the half-life lab. Okay, gotcha. So I don't have the write-up here. What part of it were you asking about? Maybe someone on here that's done it can already help you.
It was just finding the percent error. I think I have everything else. It was just, let me see, compute your percentage error by comparing it against the actual half-life of 2.55 minutes.
Gotcha. And what did you get for your half-life?
I got 2.795 for my half-life, and this is dealing with barium 137.
Yeah, that's right. Yeah, so you're just doing a 2.795 minus 2. I think it said 55.
Yeah.
And then divide it by the accepted, which is 2.55, and then move the decimal 2 places to the right.
Okay, I didn't know if it was like an actual half-life that they were looking for.
No, they're saying the accepted value is the 2.55, and yours, you can tell, being 2.7 something should be fairly close.
Okay. All right. Thank you.
No problem. Anybody else have any questions, this lab or any others for that matter? Janie, did you see the, hopefully your speaker works. Janie, did you see the actual honor code question at the end of the test? Because I've had a couple of students say they didn't see it.
No, it wasn't on there.
Okay, no problem. I figured, I think I know what happened. There's a extra step when you put a question in. I might not have did that extra step, just thought it was there. What I'm gonna do is probably get y'all to send me an honor pledge, handwrite it, and just email it to me. Handwrite it and sign it. So don't worry about
Yeah, I
that.
apologize for the abundance of emails I sent you.
Oh, that's no problem. It's actually saved me. You and a couple other people said, "Oh, I can't find the test," and it saved me because I'd put it in the right place and I turned it on at the right time, but I didn't realize if you don't have it published, it won't show it even though I set the clock to turn it on at that time. So that was, my screw up. But luckily, I think it took care of itself. Were you able to do it in the 80 minutes that you were allowed?
Oh, yeah.
Good deal. All right. Well, anybody else have any questions?
About this honor pledge, do you just want us to get a generic one off the internet or just the one that comes in the policies or what?
I'll send you one that you just handwrite and send back to me.
Okay, sounds good.
No problem. Y'all have a good one, folks, and stay safe. Don't let Rona get you.
Same to you.